After the discovery of the Higgs boson and gravitational waves, two of the most fundamental questions of physics still remain unanswered: the origin of dark matter and the origin of ordinary matter in the universe. To address the origin of matter, we have developed a technique to model first-order phase transitions in the early universe which are thought to be the cause. Amazingly, these first-order phase transitions are very similar to the phase transitions we experience daily. Take boiling water for example. Just as bubbles of steam form as we boil water, which is the new phase, bubbles of a new phase of space can form when the temperature of the universe drops from a higher temperature to a lower temperature. These bubbles form in the middle of the old phase of space in random spots, and they grow and propagate outwards. As these bubbles collide, they produce detectable gravitational waves which can shed light on the origin of matter. Our approach reformulates the bubbles' equations of motion, which are described by quantum fields, in a simpler path trajectory problem using a coordinate shift called intrinsic coordinates. The problem can now be thought of as a particle rolling down an inverted potential, where the question that you need to ask is, where should you place a particle such that it can roll down one hill and come to rest on top of another? This problem becomes increasingly more difficult to generalize in higher dimensions as the path it takes becomes a lot more convoluted. And in addition to this, the system's friction reduces over time, making the system more and more slippery. Our method looks at creating an initial guess trajectory between the first hill and the second hill, then iteratively pushing the path to the path of least resistance. At the same time, another algorithm is used to find the correct starting position using an overshoot-undershoot method, just to find the exact amount of energy so that the particle will roll down on top of the other hill metastably. In creating this model, we are one step closer in creating a larger simulation which will allow us to find the result of colliding bubbles and find the gravitational waves, which will allow us to find the fundamental question, the origin of matter. Hi everyone, thank you for watching that video. Now we'll delve into a little bit more of a technical summary of modeling phase transitions in the early universe. So, first we'll start with the objectives of what my model aims to do, and then the reformulated bubble equations of motion, the 1D algorithm, and then the 2D algorithm, and we'll finish off with a short clip of the results. So, the objectives of this project was to develop a 1D solution and a 2D solution to the this path trajectory problem that we have, or the bubble equations of motion. And then from the 2D solution, we tested and improved the stability of the solution as well as its convergence speed. So first, we reformulate the bubble equations of motion in a tangential equation and a normal equation. So the tangential equation here up at the top describes the position of the particle at any given time. So this x variable here is a trajectory that the user initially gives the program. So you guess a trajectory from the highest hill, or the true vacuum as we call it, and the lower hills, or the false vacuum, and this tangential equation will result in the position of that particle on this trajectory with respect to time. The normal equation, on the other hand, gives you the normal force that the particle experiences on the trajectory. So say we at some point here, the particle will experience some normal force which will attempt to push it off the path. So this normal force is essentially the normal force you need to push onto the particle to keep it on that trajectory. For our code to work properly, we require that the normal force is 0, so there's no force trying to push the particle of the trajectory that it takes. So let's first start with the simple 1D algorithm. The 1D algorithm is just in its crux a overshoot undershoot method. So let's start by drawing two hills here in one dimension. And so here is the high hill, or as we'll call it, the true vacuum hill. And then this is the lower hill, or the false vacuum hill. And so the problem requires us to place a particle somewhere along this hill such that it rolls down and remains at the false vacuum metastably, meaning that it remains here for a very long period of time. So what our solution does is that it looks at positions between the highest point of the true vacuum hill, so the peak, and the peak of the false vacuum hill here, and it starts off at the midpoint. And so it tests this as the starting position of the particle and sees if the particle overshoots the false vacuum hill or undershoots it. And so depending on this, it'll move the position of the particle higher or lower to give it more potential energy or less potential energy as required. This is done iteratively until it gets a stable enough solution, and then it decides yes in the convergence block, the convergence decision block, and goes straight to the action calculation. This action calculation, for all intensive purposes, is a validation technique that we can use to check if we're reaching the right a solution similar to others in literature. And now we'll have a look at the 2D algorithm. So here the 2D algorithm is a little bit complex. First thing you'll see here, however, is that the 1D algorithm is incorporated in our 2D algorithm. And this is because the tangential equation is basically the look of the equations of motion in one dimension. So if we go back, you wouldn't expect to see a normal force on this path. So it's just essentially the tangential equation. Okay, so first we start the algorithm and we go straight into the maximum finite potential rescaling / normalizing block. What these blocks do is that for any given hills, or true vacuum and false vacuum hill, it pushes those into known positions. So we make the true vacuum hill always at 1, 1, and the false vacuum hill is always given or rescaled to 0, 0. This is just for a simplification for all our functions, and it makes us easier to compute some of the properties. And then we go straight to the spline interpolation block. So this is the block which draws a trajectory between the true and false vacuum. So say we have the false vacuum here and the true vacuum here. This spline interpolation block, given a couple of control points, will give a path towards the false vacuum. This path is then parameterized by the variable x, and then we do normal and tangential vector calculations, and then we run the 1D algorithm. So the 1D algorithm will calculate the position of the particle along the path that we give it with respect to time, and then it will push a part of that solution to the normal force calculation to calculate the normal force on the whole trajectory. So then we check if the normal force is 0. If it's not 0, we use this path deformation algorithm. And so this path deformation algorithm will push the path to the path of least normal force. So if, say, we have a force pushing the particle at some point to this point here, then the next path should look something a little bit more like, say, this. And then we iterate this algorithm to push the trajectory until there's 0 normal force, and then we move to the action calculation block so that we can validate it with other techniques in literature. That brings us to the end of the technical summary. Here's a short clip of the 2D algorithm running. As you can see, at every iteration the spline is deformed, the normal force is reduced, and the initial starting position is changed. In the future, this program will be required to handle an arbitrary number of dimensions, so the problem will become quite a bit more complex. And in addition to this, it will be subject to potentials which have numerous hills. This path trajectory reformulation, however, does provide a very promising way to handle these more complex problems. So we hope that as we make this more and more complex, we will not need to change our reformulation. Lastly, I'd like to thank all my supervisors, Professor Chapa Ballas, Dr. Andrew Fowley, and Professor Marlon Pramaratna for making this whole project possible. I hope you enjoyed this video and thank you for watching. If you have any questions, please ask me.